Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 1.6 on miscellaneous equations. Alright, so there are going to be 5 types of equations in total in this section, and we're just going to jump straight into the first with an example, because this is going to be on factoring higher degree polynomials. And all of this is the same factoring techniques that we originally looked at back in section P5. So if you're a little bit rusty on your factoring, make sure you go back and review P5. So in particular, things to watch out for with higher degree polynomials. So we're looking at polynomials greater than quadratic, so cubic, quartic, whatever you might be working with. The key methods to watch out for are greatest common factor, factor by grouping, and special products. All right, so keeping that in mind, try pausing the video here and see if you can find the solutions to parts A and B of example 1. So for part A, you've got 4 terms, and you notice you've got a coefficient of 1 and 3 and a coefficient of 1 and 3. This presents as a classic factor by grouping problem. And so that's what we should try. For these first 2 terms, let's see what they've got in common. Well, no coefficient in common, but you can pull an x squared out of both terms, which would leave you with x plus 3. And then if we want to pull something out of these second 2 to make it match, it's already x plus 3. So we can just factor out a 1 to not change anything. Now you've got 2 terms with an x plus 3 in common. So if we factor that x plus 3 out, we will be left with x squared in the first term and plus 1 in the second. This is still equal to 0. All right, so we factored it now. We've got 2 factors multiplied together equal to 0. So by the zero product principle, we're going to set each factor equal to 0 and solve. For the one on the left, if you just subtract 3 from both sides, we get x is equal to negative 3. One on the right is a little bit more work. If we subtract 1 from both sides, we have x squared is equal to negative 1. So if we now apply the square root property, don't forget the plus or minus sign, x would be equal to plus or minus the square root of negative 1, which by definition would be plus or minus I. So 3 solutions. We've got negative 3. We've got plus or minus I. For part B, we've got a special product, it's called. This is a difference of perfect squares. Anytime the constant looks like a perfect square and the exponent is an even number, you can make this work. Because this is a squared squared minus 4 squared. So by our formula for a difference of perfect squares, a squared minus b squared would be equal to a plus b times a minus b. In this case, we would get a squared plus 4 times a squared minus 4 is equal to 0. Once again, zero product principle. Set each equal to 0 and solve for x, or solve for a in this case. Subtract 4 from both sides. Add 4 to both sides. Square root property twice. So for the one on the left, we get a is equal to plus or minus the square root of negative 4. Which is a plus or minus 2i. And the one on the right is just plus or minus the square root of 4, or plus or minus 2. So this equation has 4 solutions in total. We've got plus or minus 2, and we've got plus or minus 2i. Got one more to go of this type, so once again, try pausing the video here and see if you can solve part C of example 1. So this starts off like a greatest common factor method problem because we've got at least one x in each term, but these are also all even numbers, so they're guaranteed to at least have a common factor of 2. And in fact, 2 is all these are going to have in common. So if I pull a 2x out of every term, in the first term that leaves me with 15x squared. Second term, I've got 8x to the first power. And in the last term, I have a negative 12 left over. All right, we divided everything by 2 and took 1x out of each term. Now, if you see that this quadratic in parentheses factors nicely, you could keep factoring at this point. You could break that up into its factors as well. However, we got some really nasty coefficients here. It's probably not even worth it at this point. And in fact, I can tell you that this one is not going to factor very nicely. So what I'm going to do is I'm going to go ahead and apply the zero product principle now. We've got two things multiplied together equal to 0. So I'm going to set the first equal to 0. And I'm going to set the second equal to 0, all of it. And so now I've got a really easy equation to solve, because if I divide both sides by 2, 0 divided by 2 is still 0. But then I've got a quadratic equation to solve as well. So this goes back to being a problem from section 1.5. And completing the square is not going to work so great here because we've got the coefficient in front of the x squared. Again, factoring, not so good here. This is a quadratic formula problem. And so that's what we're going to do. So let's see. A little bit of scratch work off here to the side. We're going to have x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, which is a negative 12, all divided by 2 times a. We need to simplify this. Again, what I recommend when simplifying the quadratic formula is start with the square root. And in fact, I would try plugging the whole square root into your calculator first. And if it works out to be a perfect number, you're good to go. You can just leave it that way. If it doesn't, if you end up with a decimal, at that point just plug the stuff inside the square root into your calculator to simplify it into just square root of a number. And then you can try to simplify the square root from there. In this case, it works out pretty nicely though, because it turns out that the square root works out perfectly in this example because we get the square root of 784, which happens to work out to be 28. All right, so we've got negative 8 plus or minus 28 over 30. So let's see. No square roots, so we're expected to simplify this. We've got one solution, which is a minus 8 minus 28 over 30, and one that is a minus 8 plus 28 over 30. A little bit more work out to the side. For the one on the left, that would give you a negative 36 over 30. Both of those are divisible by 6, so we would get a negative 6/5 if we reduced. And for the one on the right, that would give us a 20 over 30, which if you divide both the top and bottom by 10, would reduce to 2/3. So for the quadratic formula on the right, we get two solutions, negative 6/5 and 2/3. But once you get here, don't forget that we had another solution as well from the 2x on the outside. So this equation has 3 solutions in total. We've got negative 6/5, 0, and 2/3. Next up, we've got our second type of problem in this section, and this is going to be square root equations. And so what we're looking at here are specifically equations with variables under the square root, and we want to solve for those variables. So the process for solving these is pretty straightforward, but it does have a twist we need to worry about. And the basic idea is that if you want to solve an equation like square root of x is equal to 2, if you want to get rid of the square root, you just square both sides. All right, so that's a really basic example of a square root equation. The problem is they can get a lot more complicated than that. So the process we're going to follow is like this. First things first, before you can square both sides to get rid of the square root, that only works if you just have the square root on one side of the equation. So step one is to isolate the radical. Get the square root on the side by itself. If there's more than one square root in the problem, then just focus on one to get rid of first. Isolate one of the square roots. Once you've got it on the side by itself, you square both sides of the equation to get rid of the square root, but be careful, that often means that you've got to do foiling or other things on the other side of the equation. And then step 3 is, if you still have a square root in the problem, so this would happen if you had, say, multiple square roots, you repeat the process. So you would isolate one square root, square both sides, that square root will be gone, but this one will still be sticking around. You'll see why when we work an example a little bit later on. Then repeat, isolate that square root, square both sides. Once you get to the end, you've gotten rid of all of the square roots. At that point, you'll have a linear or a quadratic equation, something of that nature to solve. So you'll solve, but you also have to check for something called extraneous solutions. These are false positive solutions. They're things that look like they work based off of the process we used here, but they actually, if you plug them back into the original equation, don't work. And the reason why those pop up in this type of problem is from step 2 here, squaring both sides of the equation. That causes us to lose some sign values. So for example, I think we could all agree that -2 is not equal to +2. Those are two different numbers. But if you were to square both sides of this equation, you would get two numbers that are equal to each other. And so the idea is kind of like that. There are some x values, some variable solutions that look like they work because when you square both sides of the equation, you get two things that are equal. But if you go back to the original equation, you'll notice that they're not the same. All right, so when I say check for extraneous solutions, you take your answers, you plug them back into the original equation before you started messing around with it. If it works, you get to keep it. If it doesn't, you throw it out. All right, so let's take a look at some examples involving square root equations. So try pausing the video here and see if you can find the solution to part A of example 2. All right, so step 1, isolate the radical. Get the square root on the side by itself, which means I just need to subtract that 2 over to the other side. And then step 2, square both sides of the equation. That is not x squared minus 2 squared on the right-hand side. Don't make that mistake. Exponents don't distribute across addition and subtraction. Left-hand side's easy enough. The square just cancels out the square root, which is kind of the point. But on the right-hand side, x minus 2 squared, you have to FOIL. So if we multiply that out, that would give you x squared minus 4x for the inner and outer terms. Be careful with the sign of the last term. -2 times -2 would turn it into a plus 4. So that's an x squared minus 4x plus 4. All right, so this is a quadratic equation because we've got an x squared. So I'm going to move everything to one side, set it equal to 0. So if I subtract x from both sides, we now have x squared minus 5x plus 4 is equal to 0. And this is one that's definitely worth checking if it factors, because the numbers are nice and small here, and in fact it does factor. So you would be looking for two things that multiply to give a positive 4 and add to give a negative 5. So that would be a -4 and a -1. Always double check yourself when you factor by at least refoiling it out in your head. We would get x squared. Minus 4x minus x would be a minus 5x plus 4. So it checks out. And now I'm going to set each of these equal to 0 and solve for x. Add 4 to both sides. Add 1 to both sides. So we get x is equal to 1 and x is equal to 4. Again, it is so tempting to just put a box around this and say those are the solutions, but you can't do that. You have to check your answers in the equation. So what I'm going to do is I'm going to take them and plug them back in. Let's start by checking 4. So if we plug that back in for x in the original equation, we would have square root of 4 plus 2 is equal to 4. All right, plugged 4 in for both x's, which if we simplify would give us 2 plus 2 is equal to 4, which is true. 4 works, we get to keep that one. Now let's check x is equal to 1. So if we plug 1 in for both x's, we get square root of 1 plus 2 is equal to 1. Square root of 1 is just 1. So this gives us 3 is equal to 1, which is clearly not true. That doesn't work. 1 in this case is extraneous. And again, the idea for that goes to the fact that we lost sign values. If you take it and plug it back to, so if I just subtracted 2 from both sides of this again, we would have square root of x is equal to x minus 2. If you were to plug in x is equal to 1, it would simplify to 1 is equal to -1, which is not true, but it popped up as a solution because we squared both sides of the equation to get rid of the square root. So anytime you square both sides of an equation, be on the lookout for extraneous solutions. All right, so let's take a look at one more. This one is a step up in difficulty. It's going to have a few more steps to it. So once again, try pausing the video here and try working part B of example 2. All right, so again, the process is isolate a square root, square both sides. Because there are 2 square roots in this equation, we're going to have to do that twice. So I'm going to start by isolating one square root. It doesn't matter which, but I like to simplify the more complicated one, if there is such a thing, first. So I'm going to start by isolating the square root of 2x plus 1. So I'm going to add square root of x to both sides. To move it across, the sign flips. And now that I've got this square root by itself, I'm going to square both sides of the equation. The left-hand side is easy because once again, the square root and the square just cancel each other out. And we get 2x plus 1. The right-hand side, though, is not 1 plus x. It doesn't work that way. Once again, because this is a binomial, we are going to have to FOIL. All right, so if we FOIL, we're going to get 1 times 1, which is 1, plus the square root of x, plus the square root of x, and then we're going to have square root of x times square root of x squared, which is just x. The 2 terms in the middle will combine to give us 2 square roots of x, so this is 1 plus 2 square root of x plus x. All right, so 1 square root down, 1 to go. So now I'm going to repeat the process. I need to isolate this square root and square both sides of the equation. So to get it on a side by itself, I'm going to subtract that 1 from both sides, and I'm going to subtract that x from both sides. Now that's going to combine with the terms on the right. 2x minus x would just give us x, and then the 1's cancel out completely. So we just get x is equal to 2 square roots of x. Now here's a little bit of a trick that will sometimes come in handy when working this type of problem. I do say isolate the radical on the side by itself before you square both sides of the equation. But truth be told, if you have a coefficient out front, you can leave that. It's okay. You don't have to get rid of the coefficients. You could divide both sides of this equation by 2, but then you're going to end up with a fraction on the other side. Instead, because of properties of square roots, or excuse me, properties of exponents, even if you have a coefficient in front of your square root, you can still square both sides of the equation to get rid of the square root. It just squares the coefficient as well. So if I square both sides of this equation now, on the left-hand side, we just get x squared, and on the right-hand side, we would get 2 squared, or 4, and if there was a bunch of stuff in the square root, we would do this in parentheses next, because it's still the coefficient times the entire square root. But in this case, we just get square root of x squared, which is x. So we get x squared is equal to 4x. All right, so this is a quadratic equation again, because we've got an x squared. So I'm going to move everything to one side, set it equal to 0. Subtract the 4x from both sides. And because there's no constant term in this quadratic equation, this is just greatest common factor. Factor the x in common out. Zero product principle. This gives us x is equal to 0. And x minus 4 is equal to 0, which if you add 4 to both sides, would give us x is equal to positive 4. All right, so these are our two potential solutions, but we have to check them. So let's start with 0. We're going to plug this back into the original equation. That would give us square root of 2 times 0 is 0 plus 1, so just square root of 1, minus square root of 0 is equal to 1. All right, so again, that's just me plugging in 0 for x, and then simplifying all that to get the 1 in the square root. And that gives you 1 is equal to 1, right? Because square root of 0 is 0, so that goes away. And so that works. We get to keep that. Let's check our other solution as well. So x is equal to 4. Once again, I'm going to simplify the inside of the square root. So if we plug in 4, this would give us 2 times 4, which is 8, plus 1 would give us square root of 9, minus the square root of just x, which we're plugging 4 in for, is equal to 1. Square root of 9 would be 3. Square root of 4 would be 2. And 3 minus 2 is in fact equal to 1. So that one actually does work out as well. So there are no extraneous solutions in this particular example, so we get to keep both solutions of 0 and 4. So the next type of equation is probably the trickiest in this section because there's a lot to keep track of. And these are going to be equations involving rational exponents. So if you've got something like x to the 2/3 power is equal to 4. And actually the square root problems that we just worked are a special case of this type of problem. So the process is going to be kind of similar to what we were just doing with square root equations. So before I walk you through the process, let's review a couple properties of exponents. The first is that if you have a power in parentheses raised to another power, you just multiply their exponents together. The second thing, which is not a property of exponents but more a property of fractions, is that if you multiply a fraction times its reciprocal, everything reduces and just gives you 1. So if we combine these two properties together, if we take a fractional exponent and we raise it to the reciprocal power, then that would give you a to the m over n times n over m, which would just be a to the first power, or a. So if you want to get rid of a fractional exponent like x to the 2/3, you can raise it to the reciprocal power 3/2, because then the exponents will multiply together to give you x to the first power. Now, this is the fastest way to solve these equations, but it's not the only way to solve it. Some students prefer breaking it up into 2 steps, and that works as well. So if I've got something like x to the 2/3 is equal to 4, we know that that exponent is telling us to do 2 things. X is being squared, and you need to take the cube root. So if you just write this in radical notation, like we did back in section P3, this would be the cube root of x squared is equal to 4, or cube root of x quantity squared. It doesn't matter which way you write it. You could cancel out the cube root by cubing both sides. That would give you x squared was equal to 4 cubed, and then you could cancel out the square by taking the square root of both sides. That's the same thing that we are doing by raising both sides to the reciprocal power. So if I have x to the 2/3 is equal to 4, if I raise both sides to the 3/2 power, this is just me doing it in one step. I am still cubing the 4 and taking the square root, just like up here. It's just doing it in one step instead of 2. But again, whatever method you prefer, however you desire to think about it, both ways work. I'm going to stick to raising both sides to the reciprocal power because, again, it's just a little bit faster. All right, so let's talk our way through the process now. Step 1 of solving an equation of the form x to the m over n is equal to k, where k is some constant, is to begin by isolating the expression with the rational exponent. Just like the first step with the square root equations was isolating the square root. Step 2, to get rid of that rational exponent, you raise both sides to the reciprocal power. All right, same thing we were doing with square root equations. If we had square root of x was equal to 2, we squared both sides. That was the same idea. We were still raising both sides to the reciprocal power. The reciprocal of square root, 1/2, just happens to be squared, 2. And then the final part, and this is the trickiest part of this problem, a lot of students forget, is that when you raise both sides to the reciprocal power, if the denominator of that reciprocal is even, you are taking an even root. So you have to include the plus or minus from the square root property. All right, so if you have x to the 2/3 is equal to 4, the one that I was looking at up here a second ago, if you raise both sides to the reciprocal power, what you're going to be doing is cubing the 4 and taking the square root. Since you are taking an even root, you have to include a plus or minus sign. So easy to forget. Be careful about that. So let's take a look at some examples involving rational exponents. Let's start with part A of example 3. X to the 4/3 is equal to 625. So first things first, the expression with the rational exponent is already isolated. We don't have to move anything around, which means if I want to get just x, I'm going to start by raising both sides to the reciprocal 3/4 power. On the left-hand side, the exponents cancel each other out, and we just get x, and this is going to be equal to, be a little bit careful here, this is an even root we're taking, so plus or minus 625 to the 3/4 power. Now, we should try to simplify this as much as we can. This is telling us to do 2 things to 625, cube it, and take the 4th root. So again, I like to start by taking the root and seeing if it works out perfectly. If it does, then you end up with smaller numbers, which is very nice. So I'm going to start by trying to take the 4th root of 625. Which, by the way, you have an X root button on your calculator that you can use for this. So you would do 4 for the X, and then you would hit X root, and then 625 in parentheses. But if you find the X root a little bit unwieldy to use, you can actually evaluate this in your calculator with a fractional exponent as well. You can do 625 to the 1/4 power. If you do, be careful though, because this exponent is pretty complicated, you're doing math in it, technically speaking, 1 divided by 4. You need to put parentheses around the exponent. This one does work out perfectly though, because 5 to the 4th power is equal to 625. So if you take the 4th root, this is going to be plus or minus 5, but that is still cubed. We're not done yet. We took the 4th root, but we haven't cubed yet. And so now I'm just going to cube 5. 5 times 5 times 5 would give us 25 times 5, or 125. So we've got two solutions here, negative 125 and positive 125. Next up in part B, we've got w to the negative 3/2 power is equal to 27. So when I raise both sides to the reciprocal power, because again it's already isolated, I'm going to include the negative sign, because again my goal is to get w to the first power. So if I've got a negative 3/2 exponent, I need to multiply that by a negative 2/3 to get w to the first power. So the negative sign is included in the reciprocal. So I'm going to raise both sides to the negative 2/3 power. Now this is not an even root this time. The denominator is 3. This is a cube root, so I do not include the plus or minus sign this time around. All right, just the one answer. So on the left-hand side, the exponents cancel and we just get w to the first power, but we need to simplify this thing on the right. First things first, this is a negative exponent, so this would be the same as 1 over 27 to the positive 2/3 power. I need to do two things. Take the cube root and square. Because 27 is 3 cubed, we can take that cube root cleanly. Cube root of 27 would be 3, but we have to square it again afterwards. 3 squared would be 9. So again, no plus or minus sign this time around because we took a cube root, so we just get one answer of 1/9. So let's take a look at two more, because again, I think this is one of the trickier types of problems in this section. Starting with part C, we've got s minus 2 all raised to the negative 1/2 power is equal to 1/3. So this one starts off pretty much like part B did. We've got a negative 1/2 power. It's already isolated, even though this is not just a single variable, it's still some expression all raised to the negative 1/2 power. We've isolated the expression. So we're just going to raise both sides to the negative reciprocal power, which would be the negative 2nd power in this case. Right? Because 2 over 1 is just 2. So on the left-hand side, that cancels out the negative 1/2 and just gives us s minus 2. On the right-hand side, property of exponents to simplify. If you have a fraction raised to a negative exponent, you can flip the fraction to turn it into a positive exponent. So negative 1/3, or excuse me, 1/3 to the negative 2nd power would be the same as 3 over 1, or just 3 squared, which would be 9. So we've got s minus 2 is equal to 9, and now all we have to do is add 2 to both sides to give us our solution of s equals 11. Part D is going to show us what happens when the solutions don't work out to be perfect integers or even rational values, like the last couple of examples. So we've got x to the 2/3 is equal to 1/2. All right, so we're going to start off by taking both sides of the equation, raising it to the reciprocal power 3/2. On the left-hand side, we just get x to the first power, which is the whole point. But again, be careful, we're taking a square root here. So this is going to be equal to plus or minus 1/2 to the 3/2 power. Now there are a couple of different ways you could apply properties of exponents to simplify what comes next. What I'm going to do is keep a few things in mind. The first is that if you have a fraction raised to an exponent, you just raise both the numerator and the denominator to that exponent, right? Exponents distribute across multiplication and division. The second thing to keep in mind is that 1 raised to any power, no matter what it is always equal to 1. So if I imagine distributing this 3/2 exponent to both the top and bottom of the fraction, then because the 1 to the 3/2 in the numerator is still just 1, I can write this as plus or minus 1 over 2 to the 3/2 power. And so now I need to do two things to this 2. I need to take a square root, and I need to cube it. And in this case, because square root of 2 is not something that simplifies exactly, I'm actually going to cube it first. So 2 cubed would give us 8, but then I still need to take the square root. So that denominator is square root of 8. Now this is a solution, but it's not in simplified radical form. So we're going to have to manipulate it a little bit. First things first, since 8 is 4 times 2, you can take the square root of the 4. So that gives us 2 square roots of 2. But now we've got a square root in the denominator still. So if I multiply both the top and bottom by square root of 2, be careful with the denominator here. So this 2 out front still sticks around, but then the square root of 2 times square root of 2 gives us another 2. So that denominator, 2 times 2, becomes 4. This is simplified radical form. It doesn't get any better than this. So we get two solutions to this problem, plus or minus square root of 2 over 4. Our next type of equations are called quadratic type equations. So they're not perfect quadratic equations, ax squared plus bx plus c is equal to 0, but they still have some expression times a constant term, and then that same expression again squared. So if u is any algebraic expression, and you've got au squared plus bu plus c, then you can still factor it like a quadratic equation. And a lot of times we'll do that by using what's called a u substitution, replacing that expression with u to get something that looks exactly like this, and then factoring like a quadratic equation before we reverse our u substitution. This actually corresponds to our factoring by substitution that's covered in section P5. Now, oftentimes this lends itself really well to higher order polynomials as well. Think about properties of exponents. If you have x raised to some power like 3, and then you square it, what would happen? Well, by properties of exponents, you would multiply those two together, and you would get x to the 6th power. So if you had some equation with x to the 6th power and x cubed, because x to the 6 is x cubed squared, you could factor this like a quadratic equation. So be on the lookout for exponents that are twice as big as ones you see elsewhere in the problem, because then you can think of it as that smaller exponent squared. With that in mind, let's take a look at part A of example 4. So we're asked to solve the following equation: x to the 4th power minus 8x squared minus 9 is equal to 0. So this is a higher degree polynomial, x to the 4th, but the first thing you should look at is what we were doing earlier in the section. Is there a way to factor this thing? Well, factor by grouping doesn't work. There's no greatest common factor here, so our only choice is to try to do a u substitution. And again, because x to the 4th power is x squared squared, we can make this work. So let's do a substitution. I'm going to let u, my new variable, be the thing that's next to the b, our x, essentially in the ax squared plus bx plus c. So u is going to be x squared, which would turn this equation into, because this is x squared squared, that is now u squared minus 8 times u minus 9 is equal to 0. And so now you want to solve this like a quadratic equation, like a problem from section 1.5. So you could do completing the square, you could do factoring, you could do quadratic formula, whatever method you prefer. This one does factor though, so that's the method I'm going to go with. I need two things that multiply to give negative 9 and add to give negative 8. Because they multiply to give a negative number, the signs are different. And what I'm looking for here is a negative 9 and a positive 1. I'm going to double check really quickly in my head. U squared checks out. Minus 9u plus u would give us a minus 8 minus 9. All right, so we're good. Now we're going to do the zero product principle. I'm going to set each of these factors equal to 0 and solve for u. Add 9 to both sides. Subtract 1 from both sides. Now don't put a box around that and call it a day, because we're not quite done yet. We weren't asked to solve this equation for u. In fact, there was no u in the problem to begin with. So now that I've factored, I'm going to reverse the substitution. I'm going to replace u now with x squared. So this is actually x squared is equal to 9, and x squared is equal to negative 1. And now if I want to solve these for x, I'm just going to use the square root property on both. So we get x is equal to plus or minus the square root of 9, or plus or minus 3. And x is equal to plus or minus the square root of negative 1, or plus or minus I. So this equation has 4 solutions in total, positive and negative 3, and positive and negative I. Now, it is worth pointing out here that the u substitution part of this process is optional. It's only to make it easier to see how it factors. But if you get really comfortable with factoring, you might be able to factor this directly into x squared minus 9 times x squared plus 1. All right, again, the idea is that you're just treating this thing that pops up twice just like you would treat x normally when factoring. So the x squared carries over instead of the x. But again, the u substitution really makes the problem a lot easier to understand, and it makes you less likely to make a careless mistake. So let's take a look at a few more examples. In part B of example 4, we've got something that looks really intimidating. We've got x squared minus x, quantity squared, minus 18 times x squared minus x, plus 72 is equal to 0. And a lot of times when students see a problem like this, they start foiling this out they'll distribute the minus 18 through, and they'll get an equation involving x to the 4th power, and they'll try to solve it. Don't do that. This is already partially factored for you. Don't undo that. Right? Because you see this x squared minus x popping up here, and the same thing popping up here squared, this is a quadratic type equation. And so I'm just going to let my u be equal to the thing in parentheses, x squared minus x. So this equation then transforms into u squared minus 18u plus 72 is equal to 0. And so now we just have a quadratic equation to solve. This one is a little bit trickier because it has larger numbers. So again, you can always use the quadratic formula as a fallback. Completing the square would also work really easily on this one because there's no coefficient for the squared term and the u term has an even coefficient. But this actually does factor, and in fact it factors into u minus 6 times u minus 12. Because negative 6 times negative 12 would give you a positive 72, and if you add them together, you would get a negative 18. And so I now set each of those equal to 0 and solve for u, which is going to give me u is equal to 6 and u is equal to 12. But we're not done yet because now we have to reverse our substitution. So this is x squared minus x is equal to 6, and x squared minus x is equal to 12. And so now, because the thing we did our u substitution on was quadratic, we now have two more quadratic equations to solve, albeit ones with smaller numbers. So these aren't quite as intimidating looking. For both, I'm going to move everything to one side and set it equal to 0. And now I'm going to check if they factor. So for x squared minus x minus 6, we're looking for two things that would multiply to give a negative 6. So that means the signs would have to be opposites. And add to give a negative 1. And what we're looking for here is a negative 3 and a positive 2. Those would multiply to give a negative 6 and add to give a negative 1. For the one on the right, we're looking for, again, two things that multiply to give a negative number. So the signs have to be opposites. Multiply to give a 12, add to give a negative 1. And so what we're looking for this time is a negative 4 and a positive 3. Those would multiply to give a negative 12 and add to give a negative 1. And so now zero product principle on both again. So we've got x plus 2 is equal to 0, x minus 3 is equal to 0, x plus 3 is equal to 0, and x minus 4 is equal to 0. So that's a negative 2. Add 3 to both sides for a positive 3. Subtract 3 from both sides for a negative 3. Add 4 to both sides for a positive 4. Basically, the sign always flips once you do the zero product principle. So this equation has 4 solutions in total. We've got a negative 3, a negative 2, a positive 3, and a positive 4. And you could do plus or minus 3 for those two if you wanted to combine them together as well. All right, so let's take a look at one more. And again, this is one that might be a little bit trickier to spot as a quadratic type equation. If you didn't know, that's what type of examples we were working right now. And again, the trick is to recognize that because 2/3 is double 1/3, right? 2 times 1/3, x to the 2/3 is x to the 1/3 squared. All right, so once again, we get 5 times x to the 1/3 squared minus 11 times our x to the 1/3 plus 2 is equal to 0. So if I let my u be x to the 1/3, then this would be 5u squared minus 11u plus 2 is equal to 0. All right, so I'm going to factor this using the British method of factoring. I'm looking for two numbers that multiply to give me a times c, 5 times 2, or 10 in this case, and add to give me b, the number in the middle, negative 11. And so the two things I'm looking for are negative 10 and negative 1. Those would multiply to give a positive 10 and add to give a negative 11. And so I'm going to break that term in the middle up. I've got 5u squared minus 10u minus 1u. All right, so the minus 11u I just broke into two parts. And then I'm going to factor by grouping. So for the first two terms, I'm going to pull out a 5u, which would leave me with u minus 2. Divide a 5 out of both, divide a u out of both. And if I also want to get a u minus 2 out of the second two terms, currently it's a minus u plus 2, so I need to swap the signs. So I'm going to factor out a negative 1. Now I've got two terms with a u minus 2 in common. So if I factor that out, it would leave me with 5u minus 1 left over. Set both of those equal to 0 and solve. We're going to get u is equal to positive 2. And for the other one, just to show a little bit more work, if I add 1 to both sides and divide by 5, we would get u is equal to a positive 1/5. But we're not done quite yet, because again, this is in terms of u right now, so I'm going to reverse my substitution. This gives us x to the 1/3 is equal to 2, and x to the 1/3 is equal to 1/5. So if I want to solve this for x, I'm going to raise both sides to the reciprocal power. The reciprocal of 1/3 is 3 over 1, or just 3. I'm going to cube both sides. And so for the one on the left, we get x is equal to 2 cubed, which is 8. And for the one on the right, we get x is equal to 1/5 cubed, which by property of exponents would be 1 cubed over 5 cubed, or 1 over 125. And so our two solutions would be 8 and 1/125. Our last type of problem in this section is going to be just an extension of what we talked about way back in section 1.1, solving more complicated absolute value equation. Now, the core idea behind the absolute value equations here are the same as they were in 1.1. So if you've got something like absolute value of u is equal to k, so as long as the absolute value is on the side by itself, then that means u is equal to k, or u is equal to negative k. The only difference is that the stuff inside the absolute value, or maybe the stuff outside, is going to be a little bit more complicated this time. So sometimes it'll turn into quadratic equations, other things of that nature. Now there is something to watch out for here. Every type of equation in this section, except for the first, has a trick to watch out for. And in this one is that if you have a variable, say an x, both inside and outside of the absolute value, the setup is still the same, but it is possible to get extraneous solutions. So you have to check under those conditions. And if you want to be safe, you can just always check your answers, of course. But anytime you plug something in and it makes the outside of the absolute value negative, you would throw that solution out, because remember, absolute value can't be equal to a negative number. An absolute value is always 0 or positive. So let's take a look at some more complex absolute value equations. So taking a look at part A of example 5, we've got the absolute value equation, absolute value of x squared minus 2x minus 16 is equal to 8. So again, the core idea is the same. We've got the absolute value of some expression equal to 8. So that means the inside of this absolute value, x squared minus 2x minus 16, would either be equal to positive 8, that would work because the absolute value of 8 is equal to 8, or the inside of the absolute value, x squared minus 2x minus 16, could be equal to negative 8 because the absolute value of negative 8 is equal to 8. And so we get two quadratic equations to solve. For both, I'm going to move everything over to one side, set it equal to 0. So I'm going to subtract 8 from both sides to give me x squared minus 2x minus 24 is equal to 0. Or add 8 to both sides to give me x squared minus 2x minus 8 is equal to 0. And so now I'm going to try to factor both. So for the one on the left, two things that multiply together to give a negative 24 and add to give a negative 2 would be a negative 6 and a positive 4. For the one on the right, we need two things that multiply to give a negative 8 and add to give a negative 2. So that would be a negative 4 and a positive 2. Set all of these equal to 0, solve for x. So we would get x is equal to negative 4, positive 6, negative 2, and positive 4. So 4 solutions in total. We got a negative 4, a negative 2, a 4, and a 6. In part B, we've got two absolute values equal to each other. And while initially that might seem like you have to handle it differently, that's not really so much the case, because let's think about this. Let's say we've got absolute value of 2 is equal to absolute value of 2. That equation would be true because 2 is equal to 2. It checks out. But similarly, if you had absolute value of 2 equal to absolute value of negative 2, that would also work because those would both give you positive 2 as well. So in other words, two absolute values are equal to each other if the stuff inside is equal or if the stuff inside is opposite. So the setup is really the exact same as if it's a number on the outside. You're going to take the inside of one absolute value, set it equal to the other side, and then you're going to take the inside of one absolute value and set it equal to negative of the other side, just like before. Now it is important to note this only works if there's nothing happening outside of the absolute values. At that point, we would be getting to equations that we wouldn't be able to solve with algebra. So that means you're not going to run into any like that. You do have to be a little bit careful here though, because when you set the inside of one absolute value equal to the negative of the other side, it has to be negative 1 times the whole side. So let's see what I mean. So for this one, I'm going to set my a minus 1 equal to the other inside of the absolute value, 2a minus 3. But I'm also going to set the inside of the absolute value, a minus 1, equal to the negative of all of the inside of the other one, negative 2a minus 3. And so that's the setup, and from here on out, it plays out pretty much the same. These are just two linear equations that are pretty straightforward. So for the one on the left, if I subtract a from both sides and combine like terms, and then add 1 to both sides, so that's 0 is equal to a minus 2, add 2 to both sides, we get a is equal to 2. Probably would have been more straightforward to just add 3 to both sides here, because then I wouldn't have had to do that last step. But we get to the same result regardless. a is equal to 2. On the other side, I distribute the minus sign through, which changes it to a minus 2a plus 3. So I'm going to start by adding 2a to both sides, and then add 1 to both sides. So we get 3a is equal to 4. Or a is equal to 4/3. So we get two solutions here, 2 and 4/3. So we're going to take a look at one more example, and this is the one you've got to be careful about, because in this problem you've got an x inside of the absolute value and you've got an x outside of the absolute value. So this is the situation where extraneous solutions can occur. But the setup of the problem is still the same. So x squared minus 6 could either be equal to positive 5x, or x squared minus 6 could be equal to negative 5x. So once again, we get two quadratic equations here. I'm going to move everything to one side, set it equal to 0. And both of these factor, so let's see. For the one on the left, two things that multiply to give a negative 6 means the signs have to be different, so plus and minus. And add to give a negative 5, so that would be a minus 6 and a plus 1. Multiply to give negative 6, add to give negative 5, checks out. And for the one on the right, we're looking for two things that multiply to give negative 6, so signs still different, but this time they have to add to give positive 5. So we have a positive 6 and a negative 1. And so if we set each of those equal to 0 and solve for x, we would get negative 1, positive 6, positive 1, and negative 6. So we've got 4 potential solutions. Negative 6, negative 1, 1, and 6. Unfortunately, they don't all work because, again, we can't have the outside of the absolute value being equal to a negative number. That doesn't work. So if we tried plugging in negative 6, you would have an absolute value equal to negative 30, which can't be the case, so that's gone. And if you plug in negative 1, you would have absolute value equal to negative 5, which doesn't work. An absolute value is always 0 or positive. It can't be equal to a negative number. So those are gone, but if you plugged in positive 1, we would get positive 5, which is fine. And if you plugged in positive 6, you would get positive 30, which is fine. And again, if you want to go a step further, very good idea if you had time on an exam and double check that these are in fact the correct solutions, you could plug it in and work out both sides of the equation and double check that they are equal to each other. You can always double check yourself when solving equations. So we actually only have two solutions here, positive 1 and positive 6. And that is it for section 1.6. So 1.6 is kind of a catch-all section. Again, even it's in the name, it's miscellaneous equations. So there's a lot of stuff going on here. The thing to watch out for is that with most of the problem types in this section, they're just tricks that you need to be careful about. Factoring higher degree polynomials is pretty straightforward. It just does require you to understand factoring techniques. There aren't really any tricks with that first problem type. But starting with square root equations, for this one, you have to check for extraneous solutions. Those pop up with this problem type because you square both sides of the equation. With rational exponent equations, you have to remember the plus or minus sign, if applicable, is how I'm going to summarize this. In other words, if in trying to solve the problem, if your reciprocal exponent has an even number as the denominator, if you're taking an even root of both sides. You don't do it for every problem, just the ones where you're taking an even root. For quadratic type equations, those don't really have a trick to them. It's mainly just about spotting when you can apply the U substitution technique. And then for more complex absolute value equations, those you have to also check for extraneous solutions. Although, if you remember that they only pop up when you have a variable both inside and outside the absolute value, that can save you a little bit of concern. But you should always check just to be safe. All right, so as always, if you guys have any questions about the material, please make sure you let me know, and I will see you in the next video.